Hi, welcome back. So in this video, we are to discuss the idea behind the two-variable regression model. So first of all, let us start with conditional mean. So put it like this. Here you have some values for capital per worker stock, like $100, $200, 3, 4, and 500 per capita. And here you have the values for income per capita, per one citizen, to be more precise. So here, in this case, you have the corresponding value of income per capita per each value of capital per worker stock. So for instance, if capital per worker stock takes the value of 100, then in the observed cases, income per capita takes the value of 1021, 1000, 950, 970, 1200, 880, and so on and so forth. So we compute the same observations for the remaining values of capital per worker stock. Now, if you calculate the average value of income per capita for this entire group, this is what you end up with. So this is overall mean for our entire sample, and we can interpret it as the expected value of income per capita. However, we can do something called conditional mean calculating. So conditional mean in this sense is similar to conditional probability. In this case, conditional mean implies that you know the capital per worker stock and you want to calculate the average income per capita value associated with this particular level of capital per worker stock. So, in order to calculate conditional mean, you have to compute the mean value for each level of capital per worker stock. So here, for instance, you calculate the mean of those values of the first column. This is the mean value of all the values of income per capita in the second column, and so on and so forth. So what you can notice here is that when you increase the value of capital per worker stock variable, then income per capita variable value increases as well. So we can conclude that there is some relationship between those variables. Higher stock of capital per worker implies higher income per capita. Okay, to make it more obvious, I put everything on a graph. So here on horizontal axis, you have capital per worker stock, and on vertical axis, you have income per capita. Again, you can notice this positive relationship. When you increase value of capital per worker stock, and the value of income per capita increases either. So yeah, in this case, we conclude on the existence of positive relationship between those two variables, which is linear or quasi-linear at the same time. And this is exactly the idea behind the linear regression. So linear regression describes how the value of conditional mean depends on the value of explanatory variable. So in this case, we analyze how the expected value of y, dependent on the value of x, or conditional mean, depends on the value of x, which serves as an independent variable. So any linear regression is expressed as a linear function where beta 0 from this formula is the value of vertical intercept. The slope of this line, or delta dependent variable divided by delta independent variable, is equal to beta 1. And yes, in this case, the function is increasing, So we can indeed conclude on the positive linear relationship between two variables. It's different from correlation because in case of correlation, we do not assume any hierarchy, but here we are stating explicitly that the value of y is dependent on the value of x. Okay, so when it comes to linear regression, let us be a little bit more specific about terminology. So there are several types of linearity. Okay, there are two of them. So linearity in terms of independent variable implies that the independent variable is linear in term. So there is a linear relationship between the dependent and independent variable. And linearity in terms of parameters means that the parameter or coefficient is linear. So for instance, what we've discussed before is linear regression, both in variables and parameters. This one is non-linear in variables because we have x squared, but linear in parameters. And this is non-linear, neither in variables nor in parameters. So each time when we discuss linear regression, we are going to stick to the first one and only occasionally to the second one. So keep in mind that linearity implies that the rate of change of the dependent variable is constant. In other words, it does not depend on the value of independent variable. Here, for instance, each time we increase x by 1 unit, y is going to increase by exactly this value. And yeah, it will not depend on the value of x. So sometimes we misinterpret it and we assume that the relationship is linear while in fact it is nonlinear. So for instance, if you consider the relationship between capital per worker and GDP per capita, according to economic theory, at least, there should be an increasing concave function. So it should go like this. However, if you collect sufficient number of observations, like we did in this case, so there are data on capital per worker and GDP per capita, and put them on the graph, you can also notice that this one does not seem to be a linear relationship. Again, it's rather concave and increasing. That's why each time you formulate a regression model, it's useful to keep in mind how this relationship should look like according to theory, and it's also useful to do some preliminary visual analysis of the data. Okay, so actually that was it. Thank you so much and see you in the next video.